I have about 13 hours left.
And his title is Cohomological Obstructions to Rational Points.
Okay, thank you very much. So before I start, I just want to say a few words. As most of you know, Ken Ribbett was my advisor. I just want to say how great it was as a young person to have somebody who not only is knowledgeable about huge amounts of number theory, but also is such a nice person. So.
Great student, too.
Oh, thank you. Okay, so I'm going to talk about the problem of deciding whether a variety over a number field or a global field has a rational point. So let me start by introducing some notation. So K will be a global field. So either a number field or a function field of a curve over a fine field. And V will be a place, and for any place V of K, KV will be the completion. And A will be the Adele ring of K. And X will be my variety. So, and I'll assume it's the nicest kind of variety. It's smooth, projective, and geometrically integral. So over K, of course. So, okay, and I'll just, from now on, I'll abbreviate all this and just say this is nice. All right, so then you can talk about we want to know whether the set of rational points is non-empty. And as a first approximation to that, you can take the adelic points. So, okay. And what this is, I mean, concretely, this is just the product over all places V of the KV points, just because X is projective. So, okay, so the first thing you could ask is whether X has a point over every completion. And if you find one completion for which it doesn't have a point, then this set is empty, and so therefore you know that that there are no rational points. So, but as we know, there are many examples where a variety has local points everywhere, but not any rational points. So the first examples were given by Lint and Reichardt. Oh, it's probably not legible. Okay, let me write it over here again. So here I'll have the adelic points, and way over here I'll have the rational points, and I'm going to ask the question for a bunch of subsets in between whether the non-emptiness imply the existence of a rational point. So imply that X has a K point, a rational point over K. And we know that the Haas principle fails. In other words, the answer here is no, that the existence of points over every completion do not imply the existence of a rational point. And the first examples were examples of genus 1 curves given in the 1940s by Lint and Reichardt. And since then, a lot of the research in this direction can be reformulated as defining certain subsets of the adelic points in which the rational points are forced to lie. And the hope is that some of these subsets might be empty even when this one's not. And so that the emptiness of this gives you another way to prove that a variety has no rational points. So some examples of these are, first, there's the set cut out by the Brouwer-Monine obstruction. So I'm going to define these. So this is a subset here. And then there's something stronger, which is the set cut out by all possible descent obstructions from all linear algebraic groups. So I'm going to define this as well. And so these turn out to be closed subsets of this set. And now you can ask whether the non-emptiness of one of these is enough to force the existence of a rational point. So in the case of the Brauer-Riemannian obstruction, it turned out that the answer is no again, as was expected. But this was proved only fairly recently by Skorbogatov. And that was, so in other words, he proved that the Brauer-Riemannian obstruction is not sufficient to answer the question whether there is a rational point. And in order to prove a set like this is not sufficient, you essentially have to come up with some new kind of obstruction, because you still if you want to have an example where this one is non-empty, but this one is empty, you have to have some way. The hard part is how do you prove that this set of rational points is empty? You have to have some other way of obstructing rational points. And so what we did was some version of a more complicated descent obstruction. So what I want to explain in this talk is this case. I want to prove that the answer here is also no, which again means that there's some new or more complicated kind of obstruction that can force the rational points to be empty, even when there are no descent obstructions from any linear algebraic groups. And this result is proved by combining an example of mine with a result of Cyril Demarche, who's a student at Orsay. And this is all done within the last 6 months. Both of our results. Okay, so I now want to explain what these sets are in between. So let me start with the Brauer-Riemannian set. So I know some of you know this well, but let me do it anyway. So the first obstruction I'm going to talk about is Brauer-Riemannian obstruction, and so for this I need to introduce the Brauer group of the variety, and this is Grothendieck's cohomological Brauer group, defined as an étale cohomology group. And in the case where X is just a spectrum of a field, this just gives you the usual, well, it's equivalent to the classical definition in terms of central simple algebras. Okay, so how do you get? In this under this hypothesis, they are. That's a theorem of, Gabor and written up by de Jong. So this is actually, in fact, it's this fact that implies that it's because these elements come from Asimai algebras that implies that any Brauer-Riemannian obstruction can be interpreted as an obstruction from some PGLN torsor. And that's what makes the descent set contained in the Brauer-Riemannian set. So, okay. All right, so let me explain how you get an obstruction from Brauer elements. So suppose you have an element of this Brauer group. So then you get a diagram like this. You can when you have an element of the Brauer group, you can evaluate it at a rational point, which an evaluation essentially means pulling back from the map from spec k into x. And using the fact that there's a contravariant functor of x. And so you get a map from x so I'll call evaluation at alpha, and it maps into the Brauer group of k. And now k is a global field, so we know what the Brauer group of k is. It fits into an exact sequence. So this is a consequence of the calculations of class field theory, that it fits into an exact sequence involving the Brauer groups of all the completions of k. And then there's a co-kernel. So it's some kind of reciprocity law tells you that this is an exact sequence. And I can make a square here by putting the adelic points here. And then if I can evaluate alpha at every component of this adelic point, in other words, at each kv point, and I'll get an element of Brauer group of kv for each v, and then I can add and then each one maps to, well, okay, so I get a map like this, and it turns out most of them are 0, so that's why it goes into the direct sum. And I can, and this commutes, and I can just draw in the composition here. So we call this phi sub alpha. And now you can see from this that there are only certain places in here where rational points can lie, namely, okay. Well, if you start with a rational point and you follow it up along the upper part of the diagram, you have to end up at 0 because that's what happens if you go down and go across. So the rational points must be contained in the following subset of the adelic points. So I'll call it XA alpha, which is just the inverse image of 0 of this map. And so each element of the Brauer group imposes a condition on the adelic points. It cuts down the locations where rational points could possibly lie. And you can do this for every alpha in the Brauer group. And so if you take all these conditions together, then you get what's called the Brauer set. It's just defined by imposing all these conditions. Okay, and by what I was just explaining, by the diagram, the rational points must be contained in this set. So then one says that one has a Brauer-Manin obstruction to the Haas principle. One says that there's an obstruction when there are adelic points. In other words, there is a kv point for every v, but the Brauer set is empty. So the Brauer group forces there to be no rational points. All right, so that's what I'm going to say about the Brauer-Manin obstruction. So now let me move on to the more general descent obstruction. So, okay. So, so I'm going to start with an algebraic group. So G will be let's say, a smooth, just to be precise, let me just say a smooth affine group scheme of finite type over K. So then I have a notion of, well, I want to define the notion of a torsor under G. So first let me define what the trivial torsor is. So, and I'll do this over an arbitrary, over a base. So a trivial X torsor under G, what does this mean? This is going to be, if X were just spec K, I just want a trivial torsor to just be a copy of G itself, with G acting by translation. But because I'm over a base, I'll just cross everything with X. So I'll take a sort of a constant family of copies of G, and then G is acting here by, let's make this, and then G is acting here just by translation. So let's say acting by right translation. On each fiber. And then a general torsor is just something that looks like that, étal locally or FPPF locally. So let me, so a general X torsor. So So the x, this always denotes the base, and the group is the thing. It's going to be the G. So this is going to be something. It's going to be some variety over x together with an action of G. So I guess, and it should such that after Étalet's projective or FPPF base extension becomes a trivial G. So I mean, if x were just spec k, this extension it just amounts to taking, for example, it's analogous to passing to an algebraic base extended to an algebraic closure, and just saying that after you base extend to an algebraic closure, it looks like a trivial torsor. So an example would be, principal and homogeneous space of an elliptic curve or something like that. Okay, but now I'm doing it over a base x, so I really have a family of these. All right. You mean it could be. I have a non-trivial extension of x, so it could be. Yeah, I'm not just twisting fiber by fiber. Right. So, okay, and these. So here's a fact. It's not a hard. Well, it's essentially consequent of FPPF descent that these if you want the collection of x torsors under G up to isomorphism, these are classified by a Galois cohomology set, H1x comma G, so which is defined. You can use Étale cohomology. Well, it's defined using Čech cocycles. Anyway, I don't want to. And so in particular, this is just general stuff about torsors. Now I want to fix one particular torsor and show how you can get an obstruction to rational points from that torsor. So let me fix y going to x under G. So let's call this f. And as an example to keep in mind, if you want to recover the classical case of two descent over an elliptic curve, you can think about the case where y is the elliptic curve and x is also the elliptic curve. And the map is the multiplication by 2 map. And this is a torsor under the two torsion group of E. So you can keep this in mind as I go through the construction of the obstruction. So, okay. So one fact about torsors over spec k is that they're trivial if and only if they have a rational point. So, and more general, maybe I should say more generally, given a rational point of the base, you can look at the fiber above that rational point, and you can get a torsor over spec k that way. So you have a natural map, defined by this torsor that I've fixed. You get a map from from x of k to h1 of k comma g. So it's k comma g, not x comma g now. And this, as I said, this is just the map that sends a rational point to the class of the torsor above it. And this gives you a partition of the rational points. You can what did I write? Oh, pi is f, yeah, that's right. So it gives you a partition of the rational points according to the class of the torsor that lies above it. And what I want to do is describe the set of rational points giving rise to a particular torsor in another way. For example, if I want the rational points that give the trivial torsor, that's the same as saying the rational points of x above which there lies a rational point of y. So that piece of the partition would just be the image of the rational points of y. And more generally, you can get the other pieces by twisting. So for any element, so sigma represents a 1 cocycle, and whose class is in H1 kg. For any sigma in this way, you can define, you get a twist of the original torsor. So it's a similar type of, it's again a torsor over X. So I'll call this map now F sigma. And well, if G is non-commutative, you might have to twist G as well, but it doesn't really matter much. But okay, so you get some inner form of G, and now I can describe what the pieces of this partition I described are. So all right, so now, what I want to say now is that if I want exactly the set of rational points having such that the class of the torsor above it is a particular element, so the class of f of x equals this fixed sigma. As in the same case, just as in the trivial case where sigma is 1, this is going to be the image of the rational points from this twisted torsor. I mean, essentially what I've done, what this twisting does, well, at least in the case where G is abelian, the fibers of this, the classes of the fibers of this are just obtained by taking the class of the original fibers and subtracting sigma from all of them. Okay, so as a corollary of this, so therefore, I mean, if you now take the union over all sigmas, you get all rational points on the left, and on the right you get a disjoint union over H1 of these images. So what this means is that if you want to know the rational points of x, you've now reduced this to the problem of finding the rational points on these possibly higher dimensional varieties, possibly infinitely many of them. So it might not seem that you're making much progress, but there are a couple of nice things that happen. First of all, well, most of these y sigmas turn out to have no idyllic points at all. So, so first of all, trivially, I can say that that this disjoint union is contained in the union over sigma. Okay, I'll just say it's the same sigma of the same thing with idyllic points. In other words, I can try to eliminate these by checking whether these y sigmas have local points. And then it turns out that condition alone already eliminates all but finitely many. So it really is just a finite union. Okay. So what's the conclusion here? So let me define a notion just to express this finiteness statement. So let me define a Zellmer set as the associated to this torsor as the set of cohomology classes. Yeah, so you can compare this with your with that example if you want to compare this to the classical Zellmer sets. So it's just the set for which these auxiliary varieties have local points. And then the theorem, so the fact that in this setup, this set is always finite. And so you really get a finite partition of the rational points. In the example, what these pieces of the partition are, well, at least they're either empty or they're cosets of 2 times e of k in this example. And then this finiteness is what gives you the weak Moirel-Vey theorem. Okay, so. So, well, there are a lot of, I mean, there all the things that you use in the, they're all first of all, they're all of the classical theorems of algebraic, I mean, the things you need to prove that the two-Selmer group on a elliptic curve is finite. So, finiteness of class group and Dirichlet unit theorem. And also there's a Borel-Serre theorem about SHA-1, or the fibers of the map from H1 KG to the product over H1 KVG, that having finite fibers. So, okay. All right, so, and now how do you get an obstruction from this? So you can get an obstruction, well, if it turns out, for example, that this set is empty, then that obstructs rational points. So that's that, and again, you can impose this. I mean, this again gives you, this thing here is a subset of the adelic points of X, and so this gives you a condition. This gives you a restriction of where the rational points can lie, and you can again impose this restriction for all torsors, and that defines the descent set. So let me define now the descent subset of the adels to be the one you get by imposing all these conditions. So you intersect over all these linear algebraic groups G and all possible torsors. And then for each torsor you get this subset on that upper right board. So you get this union over all sigma in H1 Kg of this image. Okay, and then you say, and then just as we talked about a Brouwer-Riemannian obstruction, we can talk about a descent obstruction, and we say that there's a descent obstruction when there are local points everywhere, but rational points do not exist because of the fact that this descent set is empty. Okay. Sorry? Yeah, exactly. If you impose this, if in this intersection I just restrict it to G's being the PGLNs, then you would exactly get the Brouwer-Riemannian obstruction. I mean, that's using this theorem of de Jong and Gaber that all elements of the Brouwer group come from Azimaya algebras. Okay. Now you can also combine the descent obstruction. You can combine these different kind of obstructions. So let me define now a combination obstruction where so I call it the Étale-Brouwer obstruction, where I do this descent obstruction for finite Étale groups G, but then at the end, instead of just saying, okay, the rational points of these auxiliary varieties are inside the adelic points, why don't I also apply the Brouwer-Riemannian obstruction to these auxiliary varieties? And you get further restrictions then on the locations where the rational points can lie. Well, okay. I mean, you could do it. Well, I guess one reason is that I haven't really explained what happens in the case where these auxiliary varieties are not projective. So, but I mean, you could do something where you could do a descent comma descent obstruction, and it's not clear. Actually, we still don't know whether that's equivalent to just doing a descent obstruction. I mean, if you have a torsor on top of a torsor, is it somehow dominated by some bigger torsor? We don't. I'm not sure if that's. Sorry? Yeah, you can also have descent, comma, descent, comma, descent. Descent to the infinity, yeah. Descent to the center of the earth. Okay, anyway, I just want to introduce this one now for reasons that will become clearer in a second. So, all right, so I'm not going to, so here I'm just going to take, I'm going to first apply the descent obstruction for finite étale group schemes. I mean, they're going to be étale because I assume that G was smooth. So once they're finite. Okay, so, and again, all possible torsors under these finite groups. And then for each one, I take the union over all the sigmas so I take all the auxiliary varieties. And then, but now instead of taking the image of all the adelic points, I take only the image of the Brouwer points on each auxiliary variety. So, okay, so now so how does this compare? So you can ask, how does this compare to these other obstructions? I mean, and it turns out, so it was discovered, so I asked a question in a preprint I wrote in January, whether this equals the descent obstruction. And the reason the reason I asked this is because if you, David Harari had already proved that if you restrict in this definition of the descent obstruction, if you restrict to connected algebraic groups, then it turns out that what you get is actually equivalent to the Brouwer-Meinong obstruction. So that's another reason. So you might ask, if you don't restrict to connected algebraic groups, maybe it's equivalent to this.
You only use connected G's, it's just as good as using PGLNs.
Right. It's kind of an amazing theorem that you don't gain anything by using all these, E8 or whatever. So,
Groups embed GLN and then PGLN?
well, I mean, it's more complicated than that, but
What's the special rule?
maybe, yeah, okay. I think it's in Mathematische Annalen, maybe around 2002 or so, maybe. Yeah, you'll find it. Okay. Okay, so all right. So let me describe how all these things fit together, how these things compare. So I'll have a list where I have way over on the right, on the left, I'll have the rational points, and then on the other end, I'll have the adelic points. Now, hopefully, I can fit all the things in between. Well, maybe just to be safe, I should. Yeah. Okay. All right. So let me use this too, just so I can write big. Okay, so the adelic points will be way over here now. So the first obstruction I talked about was the Brouwer-Meinong obstruction. So let's put that here. So yeah, and all these things are going to contain the rational points. And so then there's the descent obstruction. And as we've been talking about, this is equivalent to, this one is equivalent to just using the PGLNs. So this you're using more groups, you get more obstructions, so this is going to be a subset of this one. So this is the result. This is the work of consequence of the theorem of Gaber and de Jong. Okay, and now, all right, so on the other hand, well, let me copy the descent group over here. And now that now there's also the étale Brouwer group that I just introduced on the left board. And you could also imagine an étale descent where you apply the descent obstruction to these auxiliary varieties y sigma. And it's, well, just from this fact here, the fact that this is contained here, that just formally implies that this was contained in here as well. okay, so now what happened in just this year is that, Cyril Demarche, who's a student of Harari, managed to extend Harari's work to prove that actually this is contained in here. So in other words, the descent, all the descent obstructions, even if you use non-connected groups, those are subsumed by the Étale-Brouwer obstructions. So, oh, and I guess, well, this one is, I guess this one is.
But you have two, let's say, XA set. One here.
Sorry, yeah, I have a repeat.
Oh,
Yeah, and
intentional?
that's intentional because it turns out that this one's also contained in here, and this is a result of. Okay, maybe I should put some names here. So, this here was Demarche, and so is this, and building on the work of Harari and Borovoy and other people. So this is 2008, and this is also turns out to be inclusion. This is actually not quite as hard as this one. And this is quite challenging actually. You've to work with non-abelian H2 and stuff like this. Okay, so this is a result in generalizing earlier work of Stoll, who essentially proved the case that étale comma étale is the same as étale. If you have an étale torso on top of an étale torso, you can somehow find an even bigger étale torso that dominates it. It's not completely trivial, but it's quite intricate, even that case. But okay, so what's the conclusion? So if you know, as somebody noticed, this is the same group here as is here, and they're all included in each other. So that means that all these, okay, and this is contain all of them. So all of these things are equal to each other. So really, this sort of weird-looking Étale-Brouwer set that I've defined is actually the same thing as what you get by the more natural condition of using all possible linear algebraic groups. All right, so let's see. I have 20 more minutes, I think, right? All right, so let me now try to. So now okay, so this is what Demarche did. Let me now explain what I did in January. So what I did is to find an example where this set was non-empty, but still there are no rational points. So, all right. So let me well, okay. I'll write this down as a theorem maybe in a second. Yeah. So the theorem is that there exists X such that you don't get any obstruction from the Étale. The Étale-Brouwer obstruction does not rule out rational points, but nevertheless, there are no rational points. So I have to be using some kind of obstruction that's not coming from. Because of all this, the equivalence of all these, I have to be using some kind of obstruction that does not at least directly come from torsors of linear algebraic groups. So let me now explain what the strategy is for this result. So from now on, I'm going to assume. Maybe I should say the example will be for a field of characteristic not 2. I mean, this is not essential. It just makes things nicer, easier. Okay, so from now on, I'm going to assume that the characteristic of K is not 2. And so here's what I'll actually prove, and this will be a consequence of the theorem that I'll actually prove. So we'll prove Okay, so go to this board. All right. All right, so here's the theorem. So X is going to eventually be a three-dimensional variety, and it's going to be fibered over a curve. So let me start with the curve. So let C be a nice curve. So nice, again, just means smooth, projective, and geometrically integral. And I'll start any curve that has a finite number of rational points. Actually, just for this talk, I'll just assume it's just one rational point. So I'm sure you all know examples of such curves. You can easily find an elliptic curve over Q that has this property. So then, on top of this, I can build a three-dimensional variety X with the following properties. So, all right, so X is going to have a morphism down to C. So some beta here, such that okay, first of all, I need some way to make sure that X doesn't have any rational points. So the way I'll do that is just by, well, I'll say this, this is not really answering the question, but I just, for that, because C only has one rational point, I just have to make sure there are no rational points on the fiber above that 1 point P. So X sub P is the fiber above the rational point P of C. So the fiber, and I'll build this family, this X, around a counterexample to the Haas principle. So I'll have this one fiber that has a local point in every completion, but no rational point. So there are well-known examples of that. So it violates the Haas principle. And then I'll build the family around that. And okay, so now I'm already set up as far as having no rational points on X. Now I just have to make sure that is not explained by this Étal-Brouwer obstruction. So I now want to also arrange that the Étal covers of C and the Étal covers of X correspond. So in other words, every finite Étal cover of X arises from a finite Étal cover of C. So there's a natural functor from the category of finite Étal covers of C to the corresponding category for X, and I want to arrange for this to be an equivalence of categories. Sorry? Yeah, I guess so. Yeah, right. So I mean, it's right. Yeah. So this functor is just the one that takes the finite Étal cover of C and takes the fiber product. So, okay. So one last condition. So this lets me control the Étal covers of X. I know that they all come from. It will be true. Yeah, it will be true. So. Sorry? No, it's not going to be smooth. I mean, it's not going to be smooth. Yeah, X will be smooth, but X is nice.
Is XP going to be smooth?
XP will also be nice, yeah. Okay, so, and then the last condition I want to impose is that, and which is the trickiest one to arrange. But I mean, Actually, once you have the idea of doing this, it's not actually so hard to find these examples. So for all finite étale covers, if I define the pullback, if I define x prime to be the corresponding cover of x, namely the base extension, then the map on Brauer groups.
Is your C prime also nice with respect
to if there's a field, yeah, it doesn't matter. It can. I think. Oh, yeah. It should. I think. Yeah, good. That's a good question, but it shouldn't matter. Okay. I guess the answer is, I will allow it to be a finite. I'll allow arithmetic extensions in here. So it's just any finite étale cover. So, okay. So then what I want to say is then the induced map on Brauer groups is an isomorphism. So not only do C and X have the same Brauer group, but that remains true even after the finite étale extension. So this is an isomorphism. Okay, so once you have all that, then it's pretty clear what happens when you take the étale-Brauer obstruction for x. Namely, so what are the consequences of all these conditions I've imposed? So first of all, if I take the étale-Brauer set for x, that's just going to be what you get by pulling back the Brauer. You just get the conditions here by pulling back the conditions you get on C. So this is just going to be the inverse image. Well, so beta now denotes the map. This denotes the map on adelic points. Just take the inverse image of the set that's cut out by the same étale-Brauer conditions on C. But we already know that these guys can't cut out everything on C, because C actually has a rational point. So this set here is going to, in particular, it's going to contain the inverse image on the adelic points of the point P. And this is just, well, this is just exactly the adelic points on this fiber. But I said that this fiber was supposed to be a counterexample to the Haas principle. So yeah, so this is by 2 and 3. And then by 1, this is going to be non-empty. So there's no étale-Brauer obstruction for x. But on the other hand, I do also know that there can't be any rational points, because the rational points on x must all lie in this fiber above the sole rational point of C. So and that is empty by 1 again. Okay, so let's see. So I have a few minutes left. So maybe I can. Is there a question or? So maybe. Well, I'll try to do as much as I can, but I'll at least tell you what the family is. So it's going to be a family of rational surfaces over C. So the fibers are going to be rational surfaces. In fact, each fiber is going to be itself a family of conics. Each fiber is going to be a conic bundle. And the reason I'm doing that, I'm choosing that kind of family, is because at least for the simplest kind of conic bundles, there's a lot known about the arithmetic and how these obstructions work with those kind of varieties. So okay, so. So first, okay, so here's the construction. Okay, so construction. So X going down to C, there's going to be a family. Will be a family of, well, it's of what are called Chatelet surfaces, which is a Chatelet surface is a special kind of, it's a special kind of conic bundle over P1. And I'll write down more specifically what I mean in a second. So maybe I can draw a picture of this. So
It's not going to be a conic bundle over P1 bundle.
it actually will be. In fact, that's how I'm going to make it. So in fact, it'll just be a conic bundle over P1 cross C. So all right. So down at the bottom, I'll have C. Okay. So here's a curve, and it has one rational point. Maybe it'll. Okay. Maybe there. Okay. I'm trying to find a good. Okay. Okay. P, and then here I'll have C cross P1. So maybe I should move. Okay. So C cross P1, and so okay. So I know what the fiber of this above P is. Okay. So I have a copy of P1 here. So this is P cross P1. And so now I'm going to take above this. I'm going to have my threefold, which is going to be a conic bundle. So okay, there's going to be a conic bundle over C cross P1. So okay, so that means that the fibers of this map alpha are the general fiber is a smooth conic in P2. In some copy of P2, and then at some points it could degenerate, and the only way this particular family is going to degenerate is in the simplest possible way, namely, it'll degenerate to a union of two lines crossing at a point. At least, I mean, geometrically. I mean, it could be okay. All right. So the way I'll draw this, I guess, is as a. It's like a. Well, it's three-dimensional, so. All right. And so the fiber here, well, okay, I guess it's. All right. So this is supposed to be x sub p. That's the fiber there, and there's going to be a locus above here, above which the fibers are singular, and I'm going to choose that so that it intersects this blue line in 4 points. Let's choose, okay. And I'll call this degeneracy locus Z. So, all right, so this is, let's see. Okay. All right, so let me write this. So what is X? So it's going to be a smooth projective model. It's going to be a smooth projective model of something. Well, I'll write an equation for it. So it's a conic bundle given by, well, this is going to be sort of an affine equation where S, well, loosely speaking, you can think of S as being a rational function on C cross P1. Although I prefer to think about it actually for the construction, I prefer to think about it as a global section of some non-trivial line bundle on C cross P1. And then you can interpret this locally and glue it together in sort of an obvious way. So, okay, so it's going to be a global section of some line bundle. In fact, it's going to be the global section of some square of some line bundle. And that's just the square is just to make it so that there's sort of a natural way of making a smooth projective model of it. I'm not going to do the details of this, but some line bundle on C cross P1, and then such that so for most for most points of C cross P1, the S is going to take a non-zero value, and then you just get a smooth conic. But, and A, I should have said, is just an element of the ground field. A is just an element of K. And so, but where S becomes 0, this equation defines a union of two lines of slopes plus or minus square root of A. So that's going to be the degeneracy locus. So this, I'm going to assume, I'm going to arrange for this to be, for this degeneracy locus Z to be a nice curve inside C cross P1. And then the final condition is that I need to make, to prove these three conditions, 1, 2, 3, the final condition is that if you look at the fiber if you look at xp, what is that going to be? I mean, that's going to be obtained by essentially the same equation, except you restrict S to that line. And I've arranged so that it's, well, I guess I should write some other things. It's actually going to cross, it's going to cross in 4 points, and, well, I guess that's included in what I'm about to write. So when you restrict this to that line, that blue line, then what you get is it corresponds, well, this is now a section of a line bundle on P1, and so it's going to be some homogeneous binary form. And so it's going to correspond to some, well, if I dehomogenize, it will correspond to just some polynomial in one variable. And to make a so to say that this fiber is a Chatelet surface means that this is just a separable polynomial of degree 4. So, okay, so separable. Okay, separable. So distinct roots over an algebraic closure, and also, okay, and such that the surface, so now x of p is going to be a smooth projective model of y squared minus az squared equals p of x. And I want to make sure, just to get 1, I need this to violates the Haas principle. And for this, I don't need to do any just to construct this part of it, I don't need to do any extra work, because there's already back in 1971 or so, Iskovsky found an example of such a surface, of such a conic bundle with 4 degenerate fibers that was a counterexample of the Haas principle. I mean, that one is explained, well, it was explained later by the Brouwer-Meinong obstruction. So actually, there is a Brouwer-Meinong obstruction to this fiber, but the elements of the Brouwer group of that fiber do not extend to Brouwer elements of the whole threefold. So they don't explain, for x, you don't get a Brouwer-Meinong obstruction. Okay, so I think I'm out of time, so I'm not going to prove 1, 2, and 3, but it's not too hard given the setup I've given you so far. So it's just some elementary, well, okay, not completely elementary, but it's just a calculation in some sense. So, okay, I'll end here, so thank you for your attention.